Okay, so now we're going to talk about covalent bonds. And as you can see on the screen, this implies electrons are being shared. So what you're going to see in this discussion is the fact that covalent bonds result from the sharing of electrons, which is different from what we saw in the case of the formation of ionic bonds, where electrons are being transferred from one atom to another. So as stated here, a covalent bond basically consists of a shared pair of electrons between two atoms. And of all the compounds that exist, the covalent bond is more prominent and predominant compared to the ionic bond. Um, Compounds that have covalent bonds within them, they exist as discrete units that are known as molecules. So for example, in the case of carbon dioxide, CO2, basically each molecule consists of one carbon and two oxygen atoms. All right. That's a big difference between covalent compounds and ionic compounds, as I said before. You have no discrete units in the case of ionic compounds, but you do have that in the case of covalent compounds. So we don't use the term molecules when referring to ionic substances. So therefore, there is no such thing as a molecule of sodium chloride because, as stated here, in the case of sodium chloride, it consists of a large aggregate of positive and negative ions that are arranged in a particular order, and as such, there are no discrete units of sodium chloride existing. Now, we're going to look at this simple example, the simplest molecule that exists, the hydrogen molecule, which is formed as a result of the combination of two hydrogen atoms. So on this side, we have the two hydrogen atoms. Each of them have an electron in a 1s orbital. And what happens basically is that you have an overlapping of the 1s orbital. The result will be a pair of shared electrons between the two atoms, and that unit exists as a result. Now, the actual attractive force that exists comes about as a result of the attraction between the nuclei of the hydrogen atoms and the shared electrons. So it is that attractive force which constitutes a covalent bond. All right. So that's what happens in the case of the hydrogen molecule. All right. So as a result of the overlap, we end up with a shared pair of electrons between the two hydrogen nuclei. All right. So the shared electrons are most likely found here in this region between the two nuclei. And the two nuclei are shielded from each other by the electron pair, and therefore, as a result, we have the attraction between the nuclei and the shared electrons, and that's basically what holds the molecules together. There are different overlaps that can occur between p orbitals, such as what you see here. So if you have two p orbitals overlapping, you're going to end up with a pair of electrons being shared between the two p orbitals. And that is exactly what happens in the case of the formation of the chlorine molecule, right? So basically you have this p orbital overlapping with this p orbital because these single electron here from the chlorine atoms, the valence electrons, are actually located within p orbitals. So when they overlap, those electrons are shared, and again that constitutes the covalent bond. All right. So that's basically what happens. Okay, so now in the case of chlorine, each atom will now have 8 electrons on its outer shell. All right. So covalent bonding will occur with equal sharing of electrons that occurs in diatomic molecules which are formed from one element. So you know that there are certain elements that exist as diatomic molecules, right? Hydrogen, chlorine, iodine, and nitrogen. These are 4 of, I think, 7 or 8 elements that exist as diatomic molecules. So these are their representations. These are actually the Lewis symbols or Lewis structures for these molecules, right? Now, one convention that is accepted in chemistry is that you can actually use a line to represent a pair of electrons that is shared. So instead of having 2 dots between the 2 hydrogen atoms as shown here, you can have a line right here, right? And so a dash can replace a pair of electrons. So that is shown here, that is shown in this example, that is shown in that example, in the case of iodine, and also in the case of nitrogen. So it doesn't matter which representation you use. You can use either dots to represent the pairs of electrons or lines to represent a pair of electrons. All right. Okay. Here's another term that I need to introduce to you here, electronegativity. The definition of electronegativity is basically the attraction that an atom has for the shared pair of electrons in a covalent bond. So if you have two atoms connected to each other by a covalent bond, the level of attraction that an atom will have for the shared electrons, we call that the electronegativity, right? Now, if you have two atoms that are identical, they will have equal electronegativity because they will have equal attraction for the shared electrons. Now, we call this sort of bonding nonpolar covalent bonding, all right? And in the case of ionic bonding and nonpolar covalent bonding, they basically represent two extremes, because in the case of ionic bonding, you have electrons being transferred from one atom to the other, right? But in the case of nonpolar covalent bonding, you have the electrons being equally shared between the two atoms. So those represent two extremes. You can have a situation where the bonding is said to be polar, and in that situation, you have electrons being shared, but they're not shared equally, and that's because one atom is more electronegative than the other. As a result, one atom will assume what is known as a partial positive charge, right? And the other one will assume a partial negative charge. The one that is electronegative is the one that actually assumes the partial negative charge, and the one that is not as electronegative will have the partial positive charge, right? And this charge difference is a result of the difference in the electronegativities of the two atoms that are sharing the bonding pair of electrons. All right, so an example of a polar covalent bond is one that exists in the molecule HCl. The chlorine atom is more electronegative than the hydrogen, and therefore the electrons that are shared would spend its more time on average around the chlorine atom, more so than the hydrogen. And as a result, there's a partial negative charge on the chlorine and a partial positive charge on the hydrogen. All right. So that's basically what a polar bond looks like. All right. Now, as far as electronegativities are concerned, there are different ways of measuring it. I think the best method was developed by a guy by the name of Linus Pauling. He developed a scale which is largely based on thermodynamic data. And based on his scale, he came up with these numbers. There is a similar table that's available in the packet that I've posted online. So you can have access to that, and you can see the different values for the different elements. In fact, that is the scale that you'll be using in your future tests and exams. It's a 4-point scale, or the maximum value is 4, so 4 would be the highest possible electronegativity value, and that is the value for fluorine. So fluorine is the most electronegative element, and then you have some others. And what you'll find is that nonmetals tend to have high electronegativity values, while metals, their electronegativity values are low. So some trends that you'll observe: the electronegativity decreases down a group, right? Down any group, the electronegativity decreases, right? And then going left to right of any period, the electronegativity generally increases. There are some exceptions, but the general trend is that there's an increase in electronegativity going from left to right across any period. All right? So this is a version of the periodic table which shows you the metals versus non-metals, and what you'll find as far as electronegativities are concerned is that the electronegativities of metals are low, while the non-metals will tend to have high electronegativities. All right? And the polarity of a bond, right, is based on the difference in electronegativities that we saw before, right? So this is a general rule of thumb kind of information here, which shows you how to classify bonds into the category of either ionic, polar covalent, or nonpolar covalent. So what you'll find is that if there's a difference in electronegativity value between the two atoms involved in a bond, if it lies somewhere between 0.0 and 0.4, then we tend to consider those bonds to be nonpolar covalent. If the difference lies between 0.5 to 1.7, then the bond is considered to be polar covalent. And if the difference lies above, well, from 1.8 and above, then basically that bond is considered to be an ionic bond. So those are basically the criteria that we use to tell the bond category, whether or not it's ionic, polar covalent, or nonpolar covalent. So, as stated here, if the difference in electronegativity um, basically lies above 1.7, then basically the bond is ionic. All right. Um, so if it's less than 1.5, then basically the bond is strongly covalent. If the electronegativities are the same, then obviously that bond will be nonpolar covalent because the electrons will be shared equally, such as the hydrogen molecule. All right, two identical atoms bonded to each other, therefore that bond is said to be nonpolar covalent. All right, they both have the same electronegativity, so the difference will be zero. All right, so that's what happens in the case of the hydrogen molecule. It's a nonpolar covalent molecule. In the case of chlorine, the difference in electronegativity would be also zero because they're identical. So therefore, this bond would be a nonpolar covalent bond. In the case of hydrogen chloride, however, hydrogen has an electronegativity value of 2.1. Chlorine, its value is 3.0. The difference is 0.9. 0.9 is greater than 0.4, but less than 1.7. So therefore, we say that this bond is polar covalent. All right, and because it's polar covalent, we have a separation of charge where there's a partial negative charge on the chlorine and a partial positive charge on the hydrogen. And then if the difference is so large that it is greater than 1.7, such as in the case of sodium chloride, the difference is 2.1, then this bond is basically an ionic bond. What that basically means is that no electrons are being shared. Basically, there's a transfer of electrons from the sodium atom to the chlorine atom to form the ions. All right. So as we said before, when it comes to ionic compounds, there are no molecules that exist. There are no discrete units of ionic compounds. All right. Here's another definition related to polarity: a dipole. When we talk about a dipole, we're talking about a separation of charge in a bond or a molecule. Now, we're going to talk about molecules later on in terms of a dipole, but for now, what we have been talking about in terms of a separation of charge in terms of a polar bond is a dipole, right? So, for example, in the case of a hydrogen chloride molecule, that is a dipole. That bond is a dipole because you have a separation of charge due to the difference in electronegativities between the hydrogen and the chlorine atom. And we can represent a hypothetical molecule with a dipole like this, where we put a plus sign here and a minus sign here, just indicating that there are charges that are separated within that molecule. All right. Now, it turns out that a dipole can actually be measured, right? And it's also what we call a vector quantity in physics, which basically means that it has a magnitude and direction. So therefore, to indicate the symbol of, or the direction using a symbol, we use an arrow with a cross at the tail. So whenever you see that, it shows you the direction of a dipole, right? So the arrow points from the positive end of the dipole to the negative end of the dipole. So molecules such as hydrogen chloride, hydrogen bromide, and the water molecule are all polar, and we can represent the dipole direction using this symbolism. So for example, in the case of the hydrogen chloride, that's the direction of the dipole of the bond between the hydrogen and the chloride. Same thing is true for the hydrogen bromide molecule. And in the case of the water molecule, there's one dipole acting in this direction and another dipole acting in this direction. Now, the thing about water is that it has a bent shape, right? Later on, we're going to learn to predict the shape of molecules, right? But for now, you can accept that the water molecule is bent, and therefore, as a result, the dipoles within each bond will be as shown here. All right. In each case, the arrow is pointing from the positive end of the dipole to the negative end. So in other words, the arrow is pointing towards the more electronegative element of the two involved in the bond. All right. A molecule containing different types of atoms may or may not be polar depending on its shape. As I said before, we're going to learn about predicting the shapes of molecules. But for now, let's look at this molecule, carbon dioxide. Now it is known, and you're going to learn about this later on, that the carbon dioxide molecule is linear in shape, right? Now, as you can see from the structure here, the carbon here is in the middle, and it's bonded to 2 oxygen atoms at each end, right? So therefore, what you'll find is that for each bond, there's a dipole, and these dipoles will be acting in opposite directions, right? So you have one dipole acting in this direction, the other dipole acting in this direction. Furthermore, we know that the size of these dipoles are the same because this oxygen atom here would be identical to this oxygen atoms. So in this particular molecule, what you'll find out is that the dipoles will cancel out each other, all right? And as a result, the molecule itself will not be polar, even though the bonds are polar, all right? So we say that carbon dioxide is a nonpolar molecule because the dipoles within the molecule will cancel out itself, or cancel out within the molecule, all right? And we're going to see some more examples of this later on, because what you're going to find is that it's very important for you to be able to predict what the shape of the molecule is in order to predict whether or not the molecule is polar, all right? So this is again another diagram basically giving you the bond type according to the different, the electronegativity difference. And that's it for this discussion. So the next video we're going to talk about the Lewis structures of compounds as opposed to the Lewis structures of atoms. All right? Until next time.